But I can't see myself. I mean, that is there.
So we are live now. I
No,
will start. Yes, sir.
I can't see myself, but that's all right, I guess. There's no other way.
The world is full of diamonds and jewels, and we're lucky enough to have a few of them here with us today. The COVID pandemic has affected people of all ages, with students being no exception. College life has been disrupted to a large extent, but that has not stopped students in their quest for knowledge. We are delighted to welcome you all and wish you a pleasant evening. World Space Week is an annual international celebration of science and technology from the 4th to the 10th of October. We cordially invite you to the first guest lecture of Space Week 2021 organized by Pragyan in association with Nakshatra. Joining us today, we have Dr. Sanjeev Durandar as a guest of honor. Good evening, sir. Thank you for accepting our invitation. It is an honor to have you here with us today, sir.
Dr. Sanjeev Durandar is a professor at the Inter-University Center for Astronomy and Astrophysics, Pune. He also acts as the Indigo Consortium's Council's science advisor. In 2016, he received the H.K. Firodia Awards for his 3-decade-long work in exploring gravitational waves. In 1915, Einstein formulated the general theory of relativity. Within a few months, he realized that this theory implied the existence of gravitational waves which are produced due to the movement of massive bodies through spacetime. On September 14, 2015, two detectors known as the Laser Interferometer Gravitational Wave Observatory captured gravitational waves from the violent collision and merger of two black holes 1.3 billion years ago. It took 5 months for scientists to conclusively verify what they detected. To figure out what kind of astrophysical event caused the wave, the match filtering technique developed by Dr. Sanjeev Durandar and others at IUCAA was used. We now have our renowned guest, Dr. Sanjeev Durandar, with us to share his insights and views on the topic gravitational waves. Over to you, sir.
Thank you very much. Uh, Mariam, Nida Mariam, is it? Yeah. So I would like to thank the organizers for inviting me to give a talk uh, on this in this Space Week, which has been organized by Pragyan 22 NITT, and so it's very nice. This kind of programs are being organized by institutes and so on, which keeps people aware of what is going around the world, and also it makes their education, whatever they are learning in the institutes or NITT, relevant. That is the most important thing. I mean, the most. Usually the important thing is that you must know that what you are learning is actually relevant. Okay, and these kind of lectures, I think, help you to see that what you're studying now might be of importance and how it could help in the future in in this kind of endeavors where one has all these kind of projects of or scientific uh, discoveries which are taking place. Everything is required. For example, in gravitational waves, we require engineering as well as physics. Both these things are certainly have to be there. Also, mathematics and statistics, which is also important. Okay, so today's talk is on gravitational waves, past, present, and future. So it's going to be a mixture of physics as well as some of the history, which is there. Now, so I'm going to go right from the beginning because I don't expect many people to know Einstein's theory of relativity or general theory of relativity. So I'll just give a sort of a glimpse of it and whatever is relevant for this particular talk. So first thing was a century-long wait. In 1915, Einstein gave his theory of gravitation, the general theory of relativity. There you see on the right hand side his picture. He's writing his famous equations. The Ricci tensor he has written equal to zero. Okay. So these are the vacuum equations. Right? This is Einstein theory. So this was the general theory of relativity which he gave. And I will come to it, why it was required and so on. And 1916, just 1 year later, Einstein predicted the existence of gravitational waves. So he predicted these. This was one of the spectacular predictions of his theory. And in 2016, 100 years later, there was a direct detection of gravitational waves. So here are the pictures of, some diagrams which show the LIGO detectors, what is there in the data of the LIGO detectors. So there are two LIGO detectors, one in Washington, one in Louisiana in the US. One is on the northwest and the other is in the southeast of North America. And as you can see, the black holes. So in this case, what happened was that two black holes collided. They merged with each other. Two black holes went round each other. They emitted gravitational waves. These waves were detected by the detectors, and you can see the waveforms over there. And these were exactly as predicted by Einstein's theory of general relativity. So this was another feather in the cap of Einstein, that we have another proof or another sort of another evidence that his theory is correct. So we have this, and one important thing is that this is in the strong field regime. Okay, so this is the strong field regime in the sense that there were so many tests before of general theory of relativity, but they were in the weak field. So you must have heard of many of these other tests. One of them is the bending of light that was conducted in 1919 by this Eddington, actually. So Eddington was a Nobel laureate actually there, and he wanted to test Einstein's theory of relativity. And one of the ways was to see whether light bends by the right amount. And it was, and this and this was done during an eclipse. So there was a solar eclipse, and one could see a star behind the sun's disk, and the whole field of stars was distorted because of the gravitational field of the sun. And this particular observation was in fact uh, consistent, or it gave exactly the same results as what Einstein predicted. So this was one of the first tests, but this is a weak field test. Weak field in the sense that the sun's field is weak outside the sun. Okay, so the gravitational field due to the sun is weak. I can probably tell you how, in what way it is weak later on, but this is a weak field test. There were also other tests, tests like the this was before Einstein's theory gave his theory of general relativity. There was a discrepancy in the orbit of Mercury. That the Mercury's orbit, according to Newton's theory, should be an ellipse. And of course, there could be a precession because of the effects of other planets. But still, there was a discrepancy in the precision. And this discrepancy was very minute, 43 seconds of arc per century. This was the kind of discrepancy, but it was there. It could not be denied. And general theory of relativity, in fact, explained that. So there were so many other tests like that, but these are all weak field tests. So the gravitational field is weak, and because it's weak there, these tests are actually there like that. But this was actually the first test which was strong field. Two black holes colliding at almost half the speed of light, or not almost, more than half the speed of light, is a test of general relativity in the strong field, and general relativity has come through with flying colors with this test also. So this was a direct detection of gravitational waves. Okay, so the next thing is about, there were two Nobel Prizes. The first was in 1993 to Hulse and Taylor. So these are the two radio astronomers, and what they observed was a binary pulsar. That is, there are two neutron stars. These are very compact stars which were going around to each other. They emit radio waves, and these are observed on Earth. Now, what they found was that the period of these pulsars, okay, the binary pulsars, so the neutron stars were going around each other, and so there was an orbit, and that orbit had a certain period. Now, this period was going down, and this period was something like uh, uh, 8 hour period or something like that. But this was going down at a very minute rate, something like 70 microseconds per year. Okay, and they observed this pulsar for a very long time, right from more than 30 years, as you can see here on the right hand plot there. So what you see is those points there are the observations, the ones which you see as dots. But that curve which you see there is drawn from general relativity. So one has used the theory of general relativity to actually calculate how much, how the period would decrease, and the period decreases because the pulsars, as they are going around each other, they emit gravitational waves, and as they emit gravitational waves, they lose energy, and because they lose energy, they come together, they come closer together, and the period decreases. So they go faster and faster, and this is exactly as predicted, and this is an extremely accurate test, very 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 accurate test, which tells you that general theory of relativity is absolutely, I mean, seems to be extremely correct as far as this is concerned. Then there was in 2015, as I said, there was this detection, and 2016 it was formally announced that gravitational waves have been detected. And there was another Nobel Prize for the direct detection of gravitational waves by LIGO. LIGO is the detectors, are the detectors of the US. It's a acronym for Laser Interferometric Gravitational Wave Observatory. And there was significant contribution from Ayuka in India towards this discovery. And here are the Nobel laureates Kip Thorne, Rainer Weiss, and Barry Banish, who were in this field for a extremely long time. I mean, probably from the 70s or something like that. So that's more than something like 50 years ago. So what were the discoveries? So the discoveries were binary black holes and neutron stars. These are the ones which have been detected. Two black holes merging together, and this movie shows how this thing takes place. You have these two center bodies, they go around each other. As they go around each other, they emit gravitational waves. As they emit gravitational waves, they lose energy because of their emitting gravitational waves. But as the binary system loses energy, they fall more into the potential well, and they come closer together and finally merge. So this was they emits a particular waveform, and this waveform was exactly as predicted by general theory of relativity, which I have shown you before here. This is the one, which is what I have shown you on the right hand side bottom. Okay. So, and one thing which I would have to just mention is that Kip Thorne in 1986. Okay, so this is like 35 years ago. In the volume called 300 Years of Gravitation, which has been edited by Stephen Hawking and Israel. He has written an article, and he wrote an article in which he said that these were the best sources for this LIGO observatories. And this was like 35 years ago. So you can see the kind of uh, vision that he had of this kind of detection. So no doubt he deserves the Nobel Prize. And here are the detections. Okay, so here are the detections. So I would like to briefly talk about the detections. So there are the LIGO Virgo runs. So LIGO, as I said, was the two detectors in the US, and I'll tell you what those detectors are and so on. Virgo is the French or Italian French detector in Pisa. Okay, so this is a similar detector as LIGO, except it is 3 kilometers in arm length, while LIGO is 4 kilometers. And there have been three runs of this detector: O1, O2, O3. O1 was in 215 and beginning of 216, 4 months. O2 was again there for about 9 months. And O3 was for a year, which ended in 220, and it had to be stopped because of the COVID. But not too much. I mean, about a month probably before its full run. It stopped in March. It was supposed to go up to April for 31st March, but that's okay. And what were the results of this? There are many detections. About 50 black holes, binaries have been detected. Two black hole neutron star binaries, and one neutron star coalescence. So there are a whole lot of evidence that, I mean, so many events have been detected, more than 50 events. And this is what I would like to say. This is a three-in-one detection. This detection is not just gravitational waves, but this is the first direct detection of black holes. See, so far we have been saying there are black holes in the universe and so on. I mean, before gravitational waves actually discovered black holes. But these black holes were inferred. The presence of the black holes was an indirect inference. For example, we say there's a black hole sitting at the center of our galaxy. How do we know that? We know this from the Newton's third law, that a cubed omega squared is gm. That is the cube of the size of the orbit multiplied by the orbital frequency square is a constant, and that constant is g times the mass of the total mass of the system. In this case, the mass of the central system, the galaxy, turns out to be something like 4 million solar masses. Okay. And you can see stars going around this particular center. You don't see the black hole. Of course, you can't see the black hole. But you can see the orbits of the stars. And from the orbits of the stars, you can conclude what is the total mass. And the mass of the star is nothing. It is something like the mass of the sun or something like that, or a little bit more. But what you get is 4 million solar masses. And that you attribute to the black hole. And it is in a very small region. So that also can be seen because of the orbit. But there have been certain other radio observations, ultraviolet observations, which tell you that this this central object must be very small. And then what else can it be? Because if it is very small, smaller than a certain radius, and it has such a large mass, it can only be a black hole. So that's how you infer that there's a black hole. So this is how it's an indirect evidence. But gravitational waves, we saw these black holes directly in terms of this gravitational wave. You saw this waveform which were there. And the first time we have seen binary black holes. And there are so many binaries in the universe, binary stars. So there are optical binaries, which are eclipse binaries. There are X-ray binaries. There are in X-rays. There are X-ray emissions. There are this Hell-Stedler binary pulsar is a radio binary. Okay, so there are in every part of the electromagnetic spectrum you get these binaries. But this is the first time we have seen black hole binaries, and now we have 50 black hole binaries. And there have been 5 extraordinary events among these. One is this 2012, 1904, 12. See, they are labeled by the date on which they are discovered. So this is 12th April 2019. This was right in the beginning of the O3, the third run. And this is important because this is a very asymmetric masses. Asymmetric masses means that you get higher modes, which are also seen. See, the general thing, there is a quadrupole formula which tells you that there is simply a quadrupole radiation, but it's not just quadrupole radiation that comes out. Even in electromagnetism, for example, if you have a charge going around another charge, you get radiation which is in all poles, not just dipole. The same thing is here also. Here it starts at quadrupole and higher poles. But the higher poles, the radiation is much less. But in this case, if the masses are very different from each other, the higher poles are also relatively stronger. And this is important to study, get more information about the system. Then there was the 1905-21. This was the biggest black hole, okay, which was seen. And the final black hole was about 150 solar masses. So that's like what is called an intermediate mass black hole. So the black holes, the size of the black holes have been, by the size, they have been divided into different classes. So there are stellar mass black holes, intermediate mass black holes, and supermassive black holes. So the one at the center of the galaxy is a supermassive black hole because it has got a mass of more than 1 million solar masses. But these black holes, which are like less than 10, less than 100 solar masses, they are called stellar solar masses. So most of these black holes are like that. But this particular black hole has The final black hole is 150 solar masses. So it goes beyond the stellar mass and it goes into the range of IMBH, it's called intermediate mass black holes. Then there were two events which were black hole neutron star uh, coalescences. That means neutron stars which fell into the black hole. Okay, and they produced gravitational waves. So they are also important, and they could have given us a lot of information, but there's not much information in this case because I think they fell almost radially into the thing, and not there was not much other radiation which came out. But if you see the last event, 1708-17, it is a neutron star coalescence, and this was accompanied by radiation in all the entire electromagnetic spectrum from gamma ray to radio. So I'll come to that at the end of my talk. So there are all these extraordinary events which were the detections. Now let me. So this is the sort of overview which is there for the what has happened. Now I'm going into the past. Okay. So this was the present, if you like. And I'm going into the past. So let us start with Newton's gravity. I think this is what you all know, that there is the universe square law. The force is equal to minus g m1 m2 over r square into r cap. That means if you have two masses m1 and m2 with separated by a distance r, then the force is equal to m1 m2 over 1 over r square, and this is called the inverse square law because the dependence on the radius, the distance, is inverse of the distance square. So it is minus gm1 m2 r square. R cap is the unit vector, okay, pointing from one of the masses to the other, and there's a minus sign telling you that there is a attraction between the masses, and the masses don't repel each other but they fall towards each other. And g is the Newton's gravitational constant. Now I'll come to g, and that is the culprit, which that's why we could not detect this gravitational waves for 100 years. The point is that this g is extremely weak. So this is Newton's gravity. Okay, so what did Newton's gravity tell you? Okay, it explained first of all planetary orbits. So Kepler had given these laws empirically. So there are three laws of Kepler. Okay, that planets move around the sun, which are in planar orbits, which are ellipses, and so on. And then they are what the radius vector describes equal areas and equal times. And there is the third law, which I already stated, that a cubed omega square is gm. Okay, so a is the distance between the masses, omega is the circular frequency of the orbit, and m is the total mass. So these are the three laws, and these three laws were empirical. Okay, they are obtained by observations. There was no explanation. But Newton's theory, which was this his inverse square law and his laws of motion, which was the Newton's second law. So out of that we need the second law, force equal to mass times acceleration. If you use these two laws, you can cancel the m and you get a differential equation for the radius vector, which you can solve, and which tells you that all the Kepler's laws get verified. And this is there in the textbooks now, like Goldstein and all that. They tell you that that all these Kepler's laws are completely valid, are made valid just by using these two of these equations. So this is science actually. So we are progressing. So Kepler's was simply an empirical statement, but here we have a general law. Actually, we've got just two laws. We are economizing. So one thing is with science is that you economize on your number of assumptions. So the number of here there are two laws explaining maybe something like three laws or more, okay, of Kepler. So this is a step ahead. But this is not all that Newton's inverse law explained. It also explained gravity on Earth. So it explained this terrestrial gravitation. So your 2-point masses, so this was the inverse square law. And then it explained also why g is 9.8 meters per second square on the surface of the Earth. You know this thing that when you drop an object, it accelerates towards the center of the Earth and it falls with the acceleration something like 9.8 meters per second square. But this could not be explained directly in terms of F equal to minus G by in terms of the universe square law because it applied to point masses. See, in the case of this Kepler's laws or planetary orbits, the sun and the earth can be thought to be point masses because there's an enormous distance between the sun and the earth. The sun and the earth are extremely small as compared to this distance. The earth is, of course, some 10,000 kilometers or something in more than 10,000 kilometers in radius, in diameter, while the sun is about a million kilometers in radius. But both of these things are very small as compared to the distance, which is something like 150 million kilometers. So you can regard these as 2 point masses and apply this law, the universe square law. But for an object falling on the earth, this is not possible. Suppose you take something like a stone falling from something like, or an apple, as was the region, falling from say 10 meters to the surface of the earth. Now, the apple or the stone can be considered to be small compared to 10 meters, because the apple may be a few centimeters. You can consider it as a point. But the earth in no way can be considered as a point. The earth is huge as compared to the 10 meters. So then you cannot use this law directly, and one has to apply this law piecewise. You must break up the earth into small bits and take the forces from each bit of the earth and then sum them up. And when you sum them up, that sum comes out to be 9.8 meters per second square. So, and what is this sum? This is simply the integral. So, what you have to do is you have to perform a volume integral of the for the force. So, this led to the development of calculus. So, this is a extremely important step. Not only was there physics here, there was also mathematics. So, Newton had to develop his own mathematics to actually show that this law, universe square law, also applies to objects on Earth. That the terrestrial gravity is also explained through this, through his universe square law, and this took him something like a decade or 2 decades. So you can see that very serious kind of research is not something which you don't get your results in a month or 2 months or few months or a year. You have to work for decades. Okay, so that's the kind of time scale: 5 years, 10 years, 20 years. And look at gravitational wave detection also. Gravitational wave detection has started in 1960, 61 or 62 by Weber. So it has taken more than uh, 50 years or more than 50, 60 years to develop the instruments which can detect actually gravitational waves. So this is the kind of thing. This is a lesson that one must learn from these things, that one has to spend not just a year or 2 years or 10 years or a decade, maybe a lifetime, in order to actually achieve something. So, okay, so first of all, this was a grand success, this Newton's theory, because it explained two things. I mean, it was a unification in some sense. It explained terrestrial gravitation as well as it explained planetary orbits. But there was a discrepancy. See, the force law does not contain time, and see what happened in 1905 or the turn of the 20th century. Einstein gave his special theory of relativity, and that had to be given because of electromagnetism. Okay, so special theory of relativity had come to stay. And how you look at time, how you look at space, and so on was uh, was what relativity was about. So relativity basically tells you that how moving observers measure, say, masses, time, distances, energies, momenta, and things like that. So it gives you laws. It tells you what the things are, the Lorentz transformations. And in special relativity, there is no instantaneous propagation. The maximum speed at which signals can travel is the speed of light. But in Newton's theory, there was instantaneous propagation. The force law does not contain time at all. So if I shake a mass here, immediately the field will be felt throughout the universe. Changing field will be felt throughout the universe. There are no waves. Immediate, instantaneously, thing is propagated, which is inconsistent. And so Newton's theory of gravity was inconsistent with special theory of relativity. And all physics must conform to special relativity, whether it's classical mechanics, whether it's electromagnetism, or it is quantum physics. All have to be conformed to special relativity, and Newton's theory did not. This was the problem. So you needed a new theory of gravity, which was consistent with special relativity, and this was the general theory of relativity. So on to general theory of relativity. So what does general theory of relativity tell you? So this is Einstein's gravity. So Einstein's general theory of relativity is in fact a theory of gravity. So the picture changes. In Newton's theory, the sun was attracting the earth, and earth went around in orbit in the force field of the gravitational field of the sun. In Einstein's theory, the sun curves the space-time around it, and the earth moves in the straightest possible path in this curved geometry. So this is a different kind of a paradigm, if you like, or some kind of a picture where masses, energy, and things like that, they curve the space-time around it. So what are curves? Curved spaces. A sphere is a curved space. So a very simple example of a curved space is a sphere. Everybody has seen a ball, for example. So on a sphere, on the surface of a sphere, this is a curved space. It's not a Euclidean space. So it is different from Euclidean geometry because if you draw a triangle on a sphere, the angles of a triangle will not add up to 180 degrees. They'll add up to something more. So this immediately tells you that something is wrong, that it is not Euclidean geometry, that it is some other geometry. Okay. And on a surface of a sphere, you simply cannot draw a straight line. So if you go from one point to the other point on a sphere, on the surface of a sphere, you have to travel along a curve. There is no straight lines. There are no straight lines. The same thing is true in Einstein's theory. There are no straight lines. As soon as there is a gravity, you don't have straight lines. So the sun's field curves the space-time around, and the planets move along the straightest possible paths in that particular geometry. Like on a sphere, the straightest possible path would be the great circle. So the circle which passes, the plane which cuts through the center of the sphere, that will cut the sphere along the uh, along the along the great circle. So, but this is certainly not a straight line. And the planetary orbits appear curved because the space-time is curved. They are trying to travel straight, but they cannot because the space-time is curved. So now this is the paradigm, and this was the situation here. But so then now the equations have to be given. You have to tell the prescription has to be given how a given mass curves the space-time, and that is given by Einstein's equations, which are extremely complicated. So Newton's equations are very simple compared to this. It is basically a single equation. If you write it, which is the inverse square law, here there are 10 equations for 10 unknowns. 10 unknowns are the G mu nu, the metric tensor as it's called, and it is given in terms of the curvature. The left hand side is the curvature, it describes the curvature, is the Riemann tensor. On the right hand side, it is the matter, how the matter is described through what is called a energy momentum tensor. But enough about that. So, what are gravitational waves? So, as I have said, gravitation is the manifestation of curvature of space-time. So, gravitational waves are curvature, the waves in the curvature of space-time. So, the curvature as it spreads out, okay, there are ripples in the curvature of space-time. So, this is exactly what are gravitational waves. And here are the properties of the gravitational waves as given by general theory of relativity. They travel with the universal speed c, same as that of light, at about 300,000 kilometers per second. They are transverse, just like electromagnetic waves. You know, the electromagnetic wave is traveling in the z direction. The electric field and the magnetic field components, they all point in the xy plane. Okay, so they are perpendicular, orthogonal to the direction of propagation. So they are transverse, and they have also two polarization, just like electromagnetic waves, but they are more complicated because these are actually tensor waves in the in the metric. So how do you visualize these waves? So you can visualize these waves by looking at their effect on test particles. So if I take a ring of test particles, I have to take a ring because these are more complicated than electromagnetic waves. In case of electromagnetic waves, what would I have done? I would take a charge, and you have electromagnetic wave hitting a charge. The charge will oscillate. But in that case, you don't take one charge, you take a whole antenna. So where there are a whole lot of charges, so you amplify the effect with many charges which will oscillate if there's electromagnetic wave which is incident on that antenna. Here, because this wave is more complicated, you can't take just a single particle. You need to take a circle of particles, a disk, or you take a circular ring of particles. If a gravitational wave with plus polarization is incident, then it goes into an ellipse. This whole thing is deformed into an ellipse. Then again back to a circle, then back to an ellipse within for a one period of the gravitational wave. The cross polarization also does the same thing, but the ellipses are turned at 45 degrees with respect to the plus. And any general wave is a linear combination of the two, just like in electromagnetic waves. In electromagnetic waves, we have, say, suppose it's traveling in the z direction, then you have Ex and Ey are the two components. And so if you take a so Ex is one polarization, Y direction is another polarization, and you take this two linear polarization, add with a phase, you get a general electromagnetic wave traveling in the z direction. So this exactly is like this for weak gravitational waves. And by the way, we will be always be dealing with weak gravitational waves because these are the way I mean they are astrophysically generated. Why they are weak, I am coming to that. So how do you detect these waves? You can put particles on it. So just instead of putting a whole ring, you put two particles, and this will be the and if you monitor the distance between the particles, you would have measured the wave. So these two particles in the second figure, one particle has moved away, the other particle has moved closer. And if you monitor the distance between them, say with a laser, you would have, by looking at the path difference, you would be able to detect the gravitational wave. So this is the principle of detection of a gravitational wave. So this is how it works. Why did it take 100 years? So this is the basic motion of the test particles for the two polarizations. The reason why it took 100 years is because gravity is a very weak force as compared to electromagnetism or other forces. The waves are extremely hard to detect. And this is borne out by this particular thing. I don't know whether you can see. There's a glass of water. Okay. So you have a glass of water. The fact that I can raise the glass of water, okay, with my arm tells me that the gravity is an extremely weak force. Why? Because the whole earth is attracting the glass of water down. Okay, entire earth, which has so many molecules, so many atoms, while my arm, which is just made of 1 or 2 kilos of the material, it can raise this glass of water. And basically, the forces which I am using with my arm to raise are electromagnetic, because finally they are muscular forces, muscular contractions. It's coming from chemistry, and chemistry comes from electrostatics and electrodynamics. So finally, it is electromagnetism versus gravity, and electromagnetism wins even with 1 or 2 kilos as versus entire 10 to the 24 kilos or something like that, or 10 to the 24, something of that order of the Earth. So gravity is an extremely weak force, and that's why these waves are weak and they're extremely hard to detect. So G is very small. That's what it means. So you have to measure one part in something like 10 to the 22. So even if you make a interferometer, okay, which is 1 meter in size, you will have to measure distances of 10 to the minus 22 meters. So then what is the solution to this? You can't measure 10 to the minus 22 meters, it's extremely small. 10 to the minus 15 meters is the size of a nucleus, and you want to go 7 orders of magnitude below this. That's impossible. So what you have to do is you make the arms big. So that is the basic way. But let me just start with go back to what was the thing. The pioneer was Joe Weber, who started these experiments in the 60s and 70s with resonant bar detectors. So these were bars which are of aluminium or some material like that. And if the gravitational waves hit this thing, they would oscillate the bar. But the sensitivity of these bars was pretty not so good. And the better design was a laser interferometer. And this was given basically by Robert Forward in 1971. In 1971. So the laser interferometer is a better design. It's broadband, it's scalable, and also tuned to the quadrupole nature of the wave. So this is how it is. You send a laser beam inside, and then you got two mirrors here. They reflect, and finally you interfere the two beams, and then you have a photo detector on which you see this. If these mirrors move, mirrors are the test masses because of the gravitational wave. You will see a fringe shift, or you will see a detection, a wave, or flux differences on the photo detector. So this is the picture. This is the movie which tells you how this is done. So the two beams are going, they hit the end masses and they come back, the mirrors which are there. The mirrors are the test masses. So now there is nothing leaking out to the photo detector which is on the right hand side, right hand bottom. Now in this case, now there is a gravitational wave hitting this detector, laser interferometer, and the arms now oscillate. When the arms oscillate, they change, there is a path difference, and what you get is the beam leaks out onto the photo detector. And that's how you detect a gravitational wave. But note, you have to scale this effect up if you want to detect a gravitational wave because it's extremely weak. It's at the level of 1 part in 10 to the 21, 10 to the 22. So you do this by making the arms extremely big. So this is what the thing is. So you have a 4 kilometer arm length, not a 1 meter detector on the table, but a 4 kilometer arm length. So you have multiplied the length by a factor of 10,000 roughly. So immediately your problem becomes simpler by a factor of 10,000 roughly here. Then you bounce the beams several times. There's a Fabry-Pérot cavity and so on. There is a whole lot of technology which goes into this. So here is a technological feat. There are masses and there are all these. So on the left hand up corner is the mirror mass which is there. Then all these things are there. And you bounce the beams many times, maybe 100 times or 200 times in this thing. So the effective length of the arm has increased, not, it doesn't remain at 4 kilometers, but several hundred kilometers. And since you are engineering students, if this is something like 700 or 800 kilometer detector, it's like a quarter wave antenna. That is the best. It gives the best impedance match. So the wavelength that this kind of detector can detect best is at 100 hertz, or it's like 3,000 kilometers, which corresponds to something like 4 times 700 or 4 times 800 kilometers, which is 3,000 kilometers. So that's the wavelength at which it is most uh, sensitive, or the frequency is 100 hertz because they travel at the speed of light, c, which is 300,000 kilometers. But you have to guard against all sorts of noises. If you want to detect something at the level of 10 to the minus still 18 meters or 17 meters or something like that, you have to guard against all kinds of noise. And even the ground, for example, shakes at the level of 1 micron. So you must kill this noise by a factor of 10 to the 12. And mostly what one does is the left hand bottom shows you one of those isolators, seismic isolators, where you have springs and pendulums. So it is basically a low pass filter. And it kills the noise at the level of something like 1 over f square per stage. So if you have 5, 6 such stages, you get a factor of f to the 12, okay, in this thing. You keep the resonant frequency very small, of a fraction of a hertz, as compared to the frequency at which you are measuring. So generally, the bandwidth goes from 10 hertz to something like a kilohertz, and you measure the gravitational waves in this particular range, or you hope to do that. So that's the basic thing. Then there are whole thing has to be encased in vacuum and so on, because if there is air will scatter the laser light, and it will be confusion for the waves. Okay, for as I mean, you might think that they are signals. So that's why the whole thing has to be housed in vacuum, and that's the basic idea. There's a lot of technology which goes into laser optics, control systems, and so many things which are very interesting to engineers as well as physicists. So now I come to this compact binary stars. This is the source which was detected. Compact binary stars mean they are like neutron stars or black holes. Now, when I talk of neutron stars or black holes, the neutron stars have a size, they may have a mass, something like the mass of the sun, but their size is extremely small. Their size is something like 10 kilometers. Okay? So just look at this kind of thing. So while black holes are even smaller, maybe a few kilometers in size, if they are solar mass black holes. The waveform looks like this, which is drawn here. So the amplitude and the frequency first increases, finally reaches the maximum during the merge, and finally there's a perturbation, and then you can see that the thing dies off. So finally the whole thing decays, the waveform decays into this thing. So this is what you get over here. So this is the particular waveform which is there, the merger waveform. And basically here also there have been contributions. So one thing which I have to say here is that there is no analytical solution for a two-body problem in general relativity. It's too difficult. So far, even after 100 years, there is no exact analytical solution to the two-body problem in general relativity. You know there is a solution in Newton's theory because it's mathematically simpler. So here you have to do all sorts of things. You have to do approximations and all that. They are called post-Newtonian approximations. So this is so one of the people who was involved in this was Bala Iyer. For years, he was working on this with the French and the Americans, and there was a whole consortium. And along with the French collaborators, he was able to calculate. I mean, they were able to calculate these things out. Not he. I mean, it was basically the collaboration. He was part of that collaboration. So the first part of the waveform basically is the inspiral, and that is given with this post-Newtonian calculations. And the last part is in fact what is called the ring down, or the whole decays, the waveform decays until the final black hole is formed. So then this was actually pointed out by C.V. Vishweshwara in 1970. Okay, so there were contributions like this, but with the middle part you can't do anything, and you have to use numerical relativity, which is also extremely difficult. And so far, I don't think we have too many waveforms. We have something like a few thousand waveforms, and we need something like a million waveforms to actually span the parameter space. So there's a lot of active work going on in this particular field, just the theoretical work. Then match filtering the inspiral binary signal. This was the thing we gave in 1991. That suppose we had a signal, and how would you extract it from the data? So the signal looks something like this. This was just the inspiral waveform. But if you reduce this by the amplitude and put it into the noise, then you can't see anything in the middle diagram. So you look at the middle diagram, you don't see anything at all in the noise, but it is there. So how do you dig the signal out of the noise? You extract the signal by doing what is called match filtering, and this is the kind of integral that you have to perform. Xt is the data, Q of t is the filter, the match filter, and if the noise is stationary, you can solve for it in the Fourier domain, and you have the Fourier Q of f is h of f or sh of f. Sh of f is the power spectral density, and you can see that it is optimal because wherever the noise is more, this has lesser amplitude. And after the you do this kind of operation, you get a peak, okay, to this thing. So this peak occurs there, and if you put some threshold, okay, at the level of significance you want, you can say that you have detected a signal if you observe a peak like this. But the point is that there is not one match filter, because different masses of the black holes can will produce different kinds of waveforms. So something with two solar masses and three solar masses, or something with 5 and 10, will produce completely different kind of waveforms. And so all these things you must make a template bank in order to do this kind of thing. Also, your signal can come at any time, and so you have to search the data, entire data, all along the time direction. It can come with any phase. So there are so many parameters in this thing, and you have to search through the whole parameter space. So our general contribution was to how to cut down, make this whole procedure very efficient, at least with respect to searching over time and phase. So there's a symmetry in this, and we can use actually group theory, which is called this thing, to actually reduce or make the whole thing very efficient. So there was this symmetry, fast Fourier transforms and things like that can be employed, and also you can use vector spaces and things like that to actually reduce the computational cost. So how far can the detectors see? So the detectors can see. So there is a standard siren. So when the detectors, they have still not reached the full sensitivity. When the LIGO detectors reach the full sensitivity, they will be able to see 1.4 solar mass stars. These are the neutron stars, binary neutron stars, at a distance up to 600 million light years, or up to 200 megaparsecs. So this whole sphere you can see is like a map on a GPS system. This is the astrophysical map. This thing is 100 million light years, this particular thing over here. Just as you on a GPS map, you're 100 meters or 1 kilometer and things like that. This is 100 million light years. So this is 600 million light years. And so if you have such a binary star, you should be able to detect such a thing up to 600 million light years when the detector has reached full sensitivity. So far it hasn't. It has reached about three quarters with the O3 run. And the first run was in fact one third. So it was like 70, what I call 70 megaparsecs, or which is like 200 million light years, 210 million light years, or something like that. But we could see a black hole which was 1.3 giga light years, or 1.3 billion light years. How could that be possible? We could see that because the masses of the black holes were very large. They were about 30 solar masses. The larger the mass, stronger the signal. So essentially, the signal scales with the masses. So this was the event one, the first event which was seen, the first detection. There it stands above the noise. In fact, you can see the waveforms there. In the two detectors, they are basically identical. Okay, there. 36 solar mass and 29 solar mass black holes, they banged into each other. Okay, they merged into each other, producing a final mass black hole of 62 solar masses. But you can see that 36 plus 29 add up to 65 solar masses. So what happened to the three solar masses? Those went in gravitational waves. The mass has been converted into energy. This is the Einstein's equation, famous equation, E equal to mc square. Okay, so that much energy was released in the gravitational waves, and which we saw this particular waves which were here. These things don't really require match filtering to see the to detect the signal, but if you want to determine parameters and so on, you need to do match filtering. But there was another one, say I'm mentioning this. This was inside the noise. You can't see anything. So for this, one needed match filtering technique certainly to detect this particular thing. This was a event two in the first run. And there have been so many events now. More than 50 events have been detected. The next thing is, this is a very important event, which was a neutron star binary. So two neutron stars merge into each other, and this is 17th August 70. and it heralded the age of multi-messenger astronomy because it was not only the neutron stars which merged and gave out gravitational waves, there were other emissions also, gamma rays, X-rays. It was accompanied by all these emissions. So gamma rays, X-rays, UV, ultraviolet, optical, infrared, and radio. The radio observations were going on till about last year, 3 years, even after the thing. So the things were still coming out. So this actually heralded multi-messenger astronomy. And these are some of the astrophysical implications of these discoveries. What good is this detection? It's not just you have detected gravitational waves. Because these detectors act like telescopes or antennas. And you have opened a new window to the universe. So we have multi-messenger astronomy, and there was a unambiguous association of this galaxy of GW with a gamma ray with a very accurate this thing of 1 minus p equal to 5 into 10 to the minus 8. It also told you that speed of gravitational waves are wait, sorry. Speed of electromagnetic waves and gravitational waves cannot differ by more than 1 part in 10 to the 50. Although general relativity predicts that they travel the same speed, you can put a bound. And then it helped cosmology. One of the things in cosmology is to determine what is called how fast the the universe is expanding, and that is measured in terms of what is called the Hubble constant. So all the galaxies are moving away, and this Hubble constant is 70 kilometers per second per megaparsec. So if your galaxy is 1 megaparsec away, it moves with the speed of 70 kilometers per second. 70 kilometers per second away. Okay, so this is what is the thing here. Then you can get things like equation of state constraints on the neutron star because of the fact that the stars coalesce faster because of tidal deformation, because it sucks energy from the orbit and things fall into each other quicker. So you can say you can put bounds on the equation of state of neutron star matter. So there are many useful things about this. So now I come to LIGO India. Why is it a good idea? So we are building a detector in India, in Maharashtra, near Nanded. Okay. So one good thing is that the most important thing about LIGO India is it has a strategic geographical location for GW astronomy. Why? Because it is furthest away from all the other detectors in the world. It is on the almost diametrically opposite side of the LIGOs and Virgo detector and so on. So that we are so far away, and the reason and so what happens is that see these are like antennas, like dipoles, for example, in electromagnetic astronomy. You cannot say with one detector from where the signal has come. You need to triangulate the source. So you need at least 3 or 4 detectors to determine the position of the source or the location of the source in the sky. And the further away the detectors are, the better. So we are almost at a diametrically opposite end with the 39 millisecond light travel time between the LIGOs and LIGO India, LIGO detectors in the US and LIGO India, and which is slightly less than the maximum possible, uh, light travel time possible on Earth, which is like 42 milliseconds if you are exactly on the opposite sides. Of course, there are other other advantages also. That is just because it's another detector. Detection confidence, improved duty cycle, then sky coverage is better, more improve. Then you can determine the two polarizations of the wave, which is very important because the polarization confuse the distance to the source or to the binary. It's what is called degenerate with it. So if you have the polarization, you can tell what angle the black hole orientation, the spinning black hole is. So it gives more information about that. And we have a large data analysis trained manpower which exists in India thanks to the two groups in Ayuka and RRI. And of course, we have a potential large science community in the future. The lead institutes are Ayuka, IPR, the Indian Plasma Research Institute, RRCAT, that is in Indore, and DCSEM. So we have a global network of observatories around the world. We need a global, you cannot do with one detector, you need several detectors for gravitational astronomy. So what they do is they increase the detection confidence, duty cycle, source direction, and polarization, as I have mentioned. So two of these detectors are in the US, as you can see here. And one is this Virgo, which is in Italy, which is 3 kilometers. And there's a Kagra detector which has just come online now, but it has to improve its sensitivity, but should be up, which is the Japanese detector. So these are the basic ones which are there. And now we have LIGO India, which has just started. So hope it will come up by the end of this decade. So this is the situation now and the future. So I now basically come to the end of my talk. So there are existing windows which are optical, which was started by Galileo 400 years ago. So gravitational waves is a birth of a new astronomy. So it's not a one-shot experiment where you simply detect and that's the end of it. You want to do astronomy with gravitational waves. Then radio astronomy came in 1930 onwards. So already almost 100 years are over for radio astronomy. And it added to our knowledge a lot because so many things which could not be seen optically were seen in radio, like pulsars, then cosmic microwave background, quasars, all radio jets, all these were the discoveries of radio astronomy, which could not be seen optically. So as soon as you bring in a new astronomy, a new window to the universe, your knowledge of the universe increases. Now there are others like infrared, UV, X-rays, gamma rays, and also neutrino astronomy. Infrared astronomy has brought in exoplanets that we can see. There are other planets also. There are other solar systems in the universe besides ours. So these are all probes of the universe and they complement each other, all these astronomies. So now we have added another new window, which is the gravitational wave astronomy, and it is in the infant stage. So what is the future roadmap? So the current discoveries which are there, just 50, it is just the tip of the iceberg. Only a very, very small fraction of the potential sources have been detected. And this is just a fraction of the potential science of future gravitational wave observations. And there's a planned next run which will increase the sensitivity and bandwidth of the LIGO detectors. And LIGO India will join the network later in the decade. And there are also plans for space-based telescopes and some other telescope like the Einstein telescope, the underground equilateral triangle of 10 kilometers arm length, Cosmic Explorer, which is 40 kilometers arm length, with tenfold increase in sensitivity. Then there are space-based detectors like LISA, which is supposed to go, which is the ESA NASA project in 2034. They are like three freely floating spacecraft in going around the sun, heliocentric orbit, with 2.5 million kilometers arm length. So your condition on the changing in arm length becomes very much less demanding. But they operate in the range 10 to the minus 4 hertz to 0.1 hertz, as opposed to the ground-based detectors, which are from tens of hertz to kilohertz. Here I will not. Here I will stop my. So what I want to say is this is just the beginning of gravitational wave astronomy. Thank you. So I ended my talk.
Yes, sir.
So I ended my talk.
Yes, sir. Thank you, sir. That was really insightful how you explained a complex topic like gravitational waves and the working of the LIGO detector in such a simple way. We now invite the audience to post any questions they have in the chat box.
So how do I get the chat box now?
Sir, we'll be asking you, sir, like if they post it.
Okay. No questions or what?
Um,
Yeah, the thing is that how all these things, your engineering and physics and all that, all these things become relevant to all these new things. So that's the important thing to see with this.
Sir, we do have a question from Tushant M. He's asking, sir, do you think something like gravitations exist?
Yeah, that we
Gravitons.
don't know. I mean, the thing is that it's they should be there according from quantum mechanics because all matter is quantized and so on. So because matter is quantized, you must have quantum gravity. So there could be things like gravitons and all that. But these detectors and all that work at the classical level. So it's classical general relativity. I mean, the number of gravitons will be at the rate of 10 to the 30 or something like that. Uh, So it's not relevant to this to the gravitational wave detection.
Thank you, sir. That was informative.
sir, so we have another question.
Uh,
Sir, when did you realize that you wanted to enter the field of astronomy and astrophysics, and how did you develop that interest, sir? Because at the time that you got into the field, it was not a very relevant topic as such.
yeah, so I don't know. No, I was always interested in science. I mean, right from my childhood. But I got into gravitational waves as such much later. I mean, maybe 86 or something like 86. 80, yeah, found it very multidisciplinary. Actually, I heard a talk by Kip Thorne in a school, who is the Nobel laureate actually, which is there now, who won the Nobel Prize in 2017. He gave a talk on these detectors, LIGO detector. I mean, not LIGO, kilometer arm length interferometers to detect gravitational waves. And at that time, I mean, people who were listening to the talk thought that he was talking, I mean, through his hat in a way. I mean, they thought that it is completely impossible to do such a thing. I mean, it seemed such a like a science fiction. This was in '86, this 35 years back. Okay. And but I found it. I mean, I didn't really care for that whether it was fiction or not. I mean, the point was that it involved so many things. This experiment that only it involved engineering like filtering, match filtering, signal processing, and all that kind of thing. All the other physics of I mean laser optics, lasers, and all these things, vacuum systems, and so many other control systems were there. All these things there were. I mean, mechanical engineering also, seismic isolation, things like that, which are there. So it involved many branches of physics and engineering coming together, and that is what attracted me. And also there are things like, I mean, I found that, or rather, it was my contribution in a way, that much of the signal processing could be put into mathematical terms, very abstract mathematical terms, in terms of geometry and so on. So much of this batch filtering and all that, the template banks and the way we do it, we use metrics and all that. We look upon the whole thing as a differentiable manifold. So it is a so we are looking at statistical random variables and things like that. Noise is a random variable. So we are looking at certain manifolds which are in which are part of the which are like random variables and so on. So you talk of distances between signals and so on. So this was the kind of thing which I introduced uh, into the signal processing actually. Of course, this idea is not new. I mean, I came to know later that somebody in 1945 had done a similar thing. In fact, an Indian only, C.R. Rao, very well-known statistician. Okay, he's still there. He's more than 100 years old now. Okay, but, he introduced this metric in 1945, and it is basically the similar kind of metric we use for placing templates in a parameter space. But I mean, I thought it. I mean, I didn't know about this. So this work and all that. But so I introduced this on my own, and then somebody pointed out to me that it's already been done about a few years later when I was giving a talk somewhere.
Thank you, Sanix.
So we have another question. Sir, do you think India is doing enough as far as research in this field is concerned?
Enough in what in this field? Yeah, we are
Yeah.
trying our best now. So what we need is actually experimental people. I mean, we need engineers and physicists. See, the kind of groups, because I was a more a theoretical physicist or what you call things like that, and so was Bala here. The students which we have, or the whole, we have a data analysis group ready. Okay, so if we have data coming from the detector, we can analyze it. We do that anyway for the Ligo detectors and all that, which are now working. So that group is absolutely there. But sideways, but we need now experimental group, and those are being built. Like IIT Madras and all that. There is one laser people from there. CAT is there, RR CAT, and so on. So there are groups now, laser optics groups and so on, which are joining in. Groups from Calcutta and, and things like that. Yeah, and Ayuka also is now hiring a whole lot of faculty in experimental physics. So I think we are uh, taking up the challenge, but we are not quite there.
Yes, sir. For the
But we
last
should be. No. Yeah.
for the last question, are Maxwell's
Yeah.
electromagnetic laws related to general relativity theory in any way?
No, electromagnetism is I mean, it's a different interaction from gravity. So gravity is one interaction, and electromagnetism is another interaction. So it may be that if there's a unified theory, then it may be like like the Weinberg-Salam Glashow model, where they combine the two things, electromagnetism with weak. I mean, earlier, in fact, if you look at history, electricity and magnetism were two different forces. Okay, electrical forces, but then it was the unified theory was electromagnetism. Okay. Maxwell's equations. So that was the electromagnetism. But earlier, I mean, electricity and magnetism were completely different. In fact, when I was 7 or I don't know what 8 years old or something in school, I read about electromagnets and so on. And at that time, I thought that what has electricity got to do with magnetism? Electricity lights up things in the house, lights in the house, and magnetism are those magnets, horseshoe magnets, and things which stick out to the fridge or something like that. So what has electricity got to do with magnetism? So I never believed the book until I made the electromagnetic myself. So I made that electromagnet, and then I mean, it was a big discovery for me that that if you pass a current around with the wire around this thing, it magnetizes the iron rod. So it is. I mean, electricity and magnetism, for example. So this is sort of a unification. Just as Newton also unified in a way, terrestrial gravity with gravity in space. So who knows? I mean, electromagnetism and gravity may be a part of the whole one single force. But as far as it goes now, they are two separate forces. In fact, in general relativity, it is not a force at all. Okay. Gravity is not a force. It is because it's just the curvature of space-time, and objects follow the paths which are most natural for them, which are called geodesics, the shortest paths in that geometry.
Thank you, sir.
Yeah.
So we reached the end of the Q&A session. Thank you for taking time out of your busy schedule to connect with us virtually and educate our students with your immense knowledge and experience. It has been a privilege hosting you for the Space Week guest lecture series. We would like to thank everyone for joining us today. Thank you.
Thank you very much.